Good day. So in this tutorial, we're going to extend our discussion of derivatives by including functions with multiple variables. Now, the treatment is practically the same. We still need to use the rules of differentiation, and that's the reason why we're not going to take that long in discussing a couple of examples for partial derivatives. But again, the concept is still the same. The rules involving derivatives are still the same, except that there's one key characteristic when we are dealing with functions with multiple variables. In that case, when we want to take the derivative of a function, right, that has two or more independent variables, we will treat all of the other variables as constant. Hence the term partial derivative. So most of the materials are already in the slides that I have provided. So here I'm just going to show you a couple of examples that you will most likely encounter in your other economics courses. So let's try to look at, say, one of this example. Let me just show you one example, right, that involves a production function. So suppose you have a production function, which is Q. It's a function of capital and labor. And let's suppose that this production function takes on the constant elasticity of substitution form. So you have alpha, sorry, you have A alpha k raised to sigma plus 1 minus alpha L, typically which typically stands for labor. So you have 1 minus sigma, sorry, negative sigma rather, L negative sigma, which the entire term is then raised to negative 1 over sigma. All right. Pretty complex functional form, but the rules are pretty much the same, right? So, for instance, you wanted to take the partial derivative of the function with respect to the first variable k, right? Then we'll just have to treat labor L as constant. And similarly, when you want to take the partial derivative of q with respect to L, just have to treat k as a constant. Now, this partial differentiation is crucial when we talk about optimization later on, right? First order conditions require us to get the partial derivatives of each of the function with respect to all of the independent variables, set them all equal to 0, assuming, of course, that it is the stationary point of the function, in which there would be some, in some cases, the point at which the function is at its stable point, right? The point at which a function is at its most stable, right, is a point where the derivative is 0. So when the partials are all 0, then you have your first order conditions. But more on that later, right? But then again, the skill required to answer or to obtain the partial derivative of this function is still the same as the case for the first. Similar to the case of the single variable derivatives, right? So to get the partial of f or partial of q with respect to k, right? And this is the only time that you're um, compelled to use the fancy delta that you're seeing here now, right? So you can only use this partial when you're talking about multivariable functions. If you only have, say, a function with a single variable, then we don't need to use this fancy delta. So this is partial of q, partial of k, right? So we'll treat L as a constant, right? So here we have based on the structure of this function, you'll need to use some chain rule, right? So this becomes a, right? Still need to get the entire function. How do I copy this? Copy. minus 1. That's supposed to be minus 1. Right? Then you proceed to taking the derivative of the inner function. Now the thing is, since L is a constant, with respect to K, L is a constant, this term will practically disappear, right? And required required to take the derivative of this first function that has K, all right? So that would be negative alpha sigma, right? Negative alpha sigma K raised to negative sigma minus 1. Okay. And if you're not comfortable with that, you can just put this negative alpha sigma out. So you'll have equals a negative, basically negative a a alpha sigma. And then you just copy this entire expression. Copy this entire expression. Okay. And then you have K raised to negative sigma minus 1. All right. Now later on, of course, in optimization, this will become relevant. No? When you take the first order condition, try to solve for the optimal capital and labor. Normally you would see this. Normally you would see this in profit maximization problems, or in some cases you could also see this in cost minimization problems. But generally, this is you would first encounter this when you try to maximize profit function of the firm, right? So normally this will just disappear later on. But this is how your partial derivative of Q with respect to K will look like. Now, for labor, right, it's sort of symmetric, right? Since you have this outer function here, the derivative of the outer function would roughly would be identical, right? So you have your partial of Q with respect to partial of L, all right? So you will just have to copy this, right? You can just copy this entire expression, right? Because the derivative of the outer function is identical, right? Nothing changes except for the derivative for the inner function. Now, in this case, we will now treat capital as constant. Right? Now, since capital is constant, since K is constant, you'll just have to tackle with this second function. So this is going to be negative sigma, or sige, for symmetry, negative 1 minus alpha sigma, negative 1 minus alpha sigma K, or sorry, L raised to the same factor, negative sigma minus 1. All right. Or you can just move that out. Let's move that out here. So you have A just copy this entire expression. So you have A, or rather negative A 1 minus alpha sigma. Okay. And then you are left with L here. So you have L negative sigma minus 1. So don't be rattled with all of these Greek letters, because later on in your microeconomics, later in your microeconomic theory, 2 courses at that, you'll be encountering a lot of Greek letters and a lot of factors, right? Especially when you're dealing with functions that have multiple variables. So that's simple. That's one example of partial differentiation. Okay. Maybe you can have one another. Maybe you can have one more example. So again, involving again something to do with the firm. So let's have a new slide. And let's have this problem. So suppose you have the cost of cost function, right? So you have the cost of the firm, right, for producing good 1 and good 2, and it's given by A Q1 plus B Q2 plus C Q1 squared. Okay. So this is the cost function. This is the cost function of the firm producing Q1 and Q2, right? So he's producing that. The demand function for the two goods, right, which are supposed to be substitutes in consumption, is given by Q1. So this is the demand. So this is the cost. Let me just write it down for you. This is the cost, all right? This is the cost of the, maybe you can just write it. The cost of the function, the cost of producing Q1 and Q2 is given by C, AQ1 plus BQ2 plus CQ1 squared. Right, so that's your cost function. Now the demand function for the two goods are substitutes, and they're given by Q1 AP1 negative alpha 1, right, and P2 raised to beta 1. So if you're already familiar with the functional forms in economics, this is basically a reduced form of your, this looks like the reduced form of your Cobb-Douglas production function, Cobb-Douglas utility function. And you can just imagine that the quantities here are already embedded, right? But then again, the functional form looks like your typical Cobb-Douglas or an outcome of the utility maximization involving a Cobb-Douglas product, Cobb-Douglas utility function. So that's Q1. That's the demand for Q1, and the demand for Q2 is given by B P1 alpha 2 oops BP1 alpha 2 oops no alpha 2 P2, and this time he has a negative sign, right? So beta negative beta 2, right? Where obviously P1 and P2 is the price of the two goods, right? All of the constants are said to be, all of the constants are positive. All the constants are positive. Now the question is, you wanted to find the partial derivative of the cost function with respect to P1 and with respect to P2. So either we use the chain rule, right? We can use a simple chain rule, or we can just plug in the function right here and then, right? We can embed the function already, and then we solve for the partial derivative. So the task here is to solve for the partial of C, respect to P1, and the partial of C with respect to the partial of P2. Right? So that's the question. Right. Now let's look at the function more carefully. To make this easier and more straightforward, let's use chain rule. All right, let's use a chain rule, and in order for us to use that, we may want to take the partial derivative of the demand functions first with respect to the price, which we will use later on when you plug it back in your respective function. So first, let's look at partial of C with respect to P1. Right. So in general, the partial of C with respect to partial of P1 is equal to A A times the partial of Q1 with respect to partial of P1 plus B partial of Q2 with respect to partial of P1, right? Plus 2C Q1, right? Because of course you have Q1 squared here, so you take the derivative of this function with respect to Q1 first, and you'll get 2C Q1 times the partial of Q1 with respect to P1. Partial of And you just have to copy this for P2, right? We'll just have to change the indices. So you have P2 here. So you have partial of P2, right? You have partial of P2, and you have another partial of P2. Right? Now, once you have this formula, you'll just have to find this, right? Actually, just have to find two. You just have, or rather four. You have to find four functions, right? Partial of Q1 respect to P1, partial of Q2 respect to P1, Q1 on P2, and Q2 on P2. And then we'll plug this back in the function. Set this aside, and let's look for those partial derivatives. So let's look for the partial of Q1 with respect to partial of Q1 with respect to the partial of P. Partial of P1. Right? So the function is alpha P1 raised to negative alpha 1, beta P2 raised to beta 1. Right? So solve for the function. So solve for the derivative. So P2 is treated as a constant. P2 is treated as a constant, so we'll just leave it as it is. We'll just focus on P1. So that's going to be negative alpha 1 a P1 raised to negative alpha minus 1, or let's be specific, alpha 1 minus 1 P2 raised to beta 1. Oops. P2 raised to beta 1. All right, so that's your partial of Q1 with respect to P1. How about P2? Partial of P2, partial of Q1 with respect to P2 is given by, so this becomes beta 1, right? Put down with P1 is a constant now, right? P1 is a constant now, so you don't have to do any, you don't have anything to do with that. So that's going to be beta 1 a P1 alpha, right? So this -1 disappears, and you'll move it to beta. Okay. Well, if you're more comfortable, you can just, if you're more comfortable with this expression, you just say negative alpha 1 a. You have P2 beta 1 over P1. So this is negative. This is alpha. This is alpha 1 plus 1. Alpha 1 plus 1. Right. Okay. We just transformed this. We just transformed P1. Right. Now the same happens for P1. The same happens for the second equation. Right. So you just have beta 1. Now we have a fraction, so we have P2 raised to beta 1 minus 1 all over P1 raised to alpha 1. So we can just plug this in later. Now for Q2, right, the process is pretty much the same. Right? So you have partial of Q2 respect to the partial P2, P1 rather. Start off with P1, of course. You have B. So it's just this, right? It just looks like this. So the second equation, wherein the alpha is positive and beta is negative, right? So P1 is basically alpha 1, alpha 2 rather, alpha 2B, P1, alpha 2, right? And P2 is raised to negative beta 2 minus 1. Or it's similar to this equation, right? Sort of similar to the first functional form, right? So you have alpha 2 B, right? You have a fraction here, in which case that's P1 alpha 2 alpha 2, right? And then you have P2 on the bottom as the denominator. P2 beta 2 plus 1, right? That's your P1. Okay. Now for P2, right, it's gonna look like the second. It's gonna look like the second equation. So copy this. Oops. Let's just copy this. Right. So 4 equations, right? We have P2. This becomes negative beta 2 be P1 alpha 2. Sorry, this should be. Sorry. Let me erase that. Now. This should be BP1 alpha minus 1, and B2 remains the same. Negative B2 remains the same. So you have alpha 2 minus 1. So it should be similar with the second equation for Q1. Right? And you have B2. Right? Now for P2, right, you have B2 alpha, right? Negative B2, right? Negative B2, B, P1, P1, nothing happens to P1, just it's just the same as before, but this time you're going to subtract 1 from beta 2, negative beta 2, because of definition of the derivative, right? So we take the derivative of Q to respect to P2. Right? BP1 alpha 2 is constant. So keep it as it is, and keep it as it is, and then you have this expression. I just have to replace this. This just becomes negative beta 2. Okay. Now we have the 4 equations, so just have to plug them back in the derivative of C. All right. So let me copy this. Just copy this here. So what is partial of Q1 with respect to P1? And what's partial of Q2 with respect to P1? Right. So just have to copy. Right. Just have to copy everything. Everything that's related to P1, that is. So that's A. That's A. Maybe you can put a bracket here. So A Q1 over P1. So that's the first equation. Let's copy it here. Right. Plus B. So what's Q2? What's partial of Q2 with respect to P1? This expression. All right. Copy this here. Plus 2C. Well, you know what Q1 is. Q1 is P1 just add a parenthesis here. So that's A P1 negative alpha 1 P2 beta. P2 beta 1. Okay. And you have a bracketed term for, again, this partial derivative. Okay. So let me just resize this. Now it's up to you if you want to clean this up and factor things out. But then again, there's no um, there's no real benefit anyway, since all of them are in terms of P1. You cannot factor some of the items out. So normally that's fine. Right? This should be fine. Right? So for the partial of C, with respect to P2, again, it's just a matter of substituting. It's just a matter of substituting terms. Right? So this is your partial of C with respect to P1. Let's type in the partial of C with respect to P2. Okay, and then we'll have partial here. Oops. The partial of C with respect to the partial right. Partial of C with with respect to the partial P2. So that's A. What's Q1 P2? So this expression. Okay. Just copy it here. Okay. Plus Q2 over P2. So you have B Q2 P2, which is this one. Q1 P2. Right. Okay. Plus 2C Q1. I'll just copy this. And then another bracketed term. Oops. Another bracketed term here. Right, just to copy Q1. Sorry, Q1 over P2. And there you have it. All right. So this is the partial of the cost function with respect to P1 and P2. Right. Now, like the case for the derivatives of single variable functions, just a matter of practice and being comfortable seeing a lot of terms like this and being able to simplify these expressions later, if applicable, being able to simplify these expressions later on, albeit correctly, of course, right? So you'll just have to refer. So just refer to the exercise sets that I have uploaded, right? So you can have a bit of a practice, or rather the problem set that I have uploaded, so that you'll be able to practice obtaining partial derivatives. So for further questions, like I usually say, if there are other questions regarding the mechanics of this in the case of the partial derivatives, you'll just have you can just post them in our discussion groups. So till our next video, and have a good day.